Hi from Chile. I'm Jose Abel, civil engineer, and today I want to show you a new tool I just released. I've been waiting to do this video for a long time. This is something I wanted to share with you guys. It's about merging or using together OpenSeesPy with gmsh on Python. So I just released this new module called gmsh to OpenSees. It's a very simple module that contains some tools that you can use to create models in gmsh, analyze them in OpenSees, and then visualize the results in gmsh. This little figure over here was done using that module. So there's some installation instructions. I'm going to assume for this video that you know your way around your Python, that you know OpenSeesPy, that you know gmsh. We're going to be using a little bit of the gmsh Python interface, but it's all through the new module. So let's see if this can help you create some new wonderful modules. So we're going to start off by creating a geometry in gmsh. So I'm working on Linux right now. I have Sublime Text in the back over here, and I opened this terminal, which I'm just going to be using to type some commands and run some of the simulations. So I'm going to create a new gmsh model called example.geo. So in here we're just going to add a simple box, and we're going to create a little model. So this box over here, we're going to just make it a cube that is 1 by 1 by 1. Let's go ahead and add that geometry. And once you add that geometry, you can see in my folder here where I'm working, I have the example geo file, and you can see the geometry file over there. We're going to tweak this a little bit later today. But for now, we're going to stick in here. And what I want to do is, if I press the number 3 key on my keyboard, I'm going to create, by default, a tetrahedral mesh, like so. You can also do this by pressing the 3D button here, right? What I did there is I reloaded the script, which is key 0 on the keyboard. And then if you press 3D, you get the tetrahedron mesh. And by default, you get around 1,000 tetrahedra here. Depends on the algorithm you're using, but this is what you should get. So what we want to do is we want to analyze this mesh. We want to pretend it's a steel cube, and we're going to apply a load in one of the corners and just get the displacement field and visualize that. So we're going to fix the bottom and apply a load at the top. So in order to get that, I'm going to add a physical group. And I'm going to add a surface physical group. I'm going to select the bottom of the model and just let's call that fixed. Press E to escape. And then I'm also going to add a volume group. I'm going to select that little dot over there and call that the solid and escape. So now we mesh again, press number 3, and then we save that. Save this mesh, and you can see the MSH file. So the geo, you just have some code there to add the physical groups, and then when I saved, I get the mesh, which is what we're going to be using to analyze in OpenSees. Okay, so that's the simple setup we want to have. Oh, let's have some coffee. Okay, 9:30 a.m. here in Chile, so I need a little bit of coffee to get through this tutorial. Okay, so the example. Let's go on to the example. Okay, so from here, what we want to do is we want to create a model, an OpenSees model from this mesh. So if you take a look at the MSH file, you can see the nodes in here. So somewhere in here is the information about the nodes. So basically what we want to do is we want to create one node for each of these nodes in here. I'm going to enable, in the mesh, I'm going to enable the node visibility. You can see some little dots come up. So for each of these dots, we want to create a node. For each tetrahedron, we want to create a tetrahedron element and assign a material model to that. And then we want to also fix all the nodes that are at the bottom that belong to the fixed physical group. And let's also think about where we're going to add the load. I'm going to do something simple for now. I'm going to enable the node labels, and we're going to add a load at node 7. So we can go for node 249, so that it's in the middle, and roughly in the middle. It's not exactly in the middle, but so that we can get some displaced shape. Anyway, So that's what we want to do. Okay, so how do we go about this? Okay, so first let's import OpenSees. So the command to import OpenSees in Python is like this. I'm using Linux again, so under Windows it's going to be something like OpenSeesPy.OpenSees as OPS. This line may vary depending on the system. I don't know what it is on a Mac. Then we're going to import the gmsh to OpenSees library, right? So this is going to have some useful commands to interface, and we're also going to import gmsh. With gmsh, we're going to load the model. So the first thing we're going to do, import gmsh, is we're going to initialize gmsh, like so, and we're going to load the msh file. Okay, so we're going to point it to this file, and I'm going to open a terminal here so we can run some things. Here we go. If I go python example1.py, what I'm going to see is that it's reading that msh file and it's giving me some information. So up to now, nothing too fancy. We want to start creating nodes. So how do we do that? Let's start by first initializing our OpenSees model. So we'll start creating a basic builder model with 3 spatial dimensions and 3 degrees of freedom per node. And then after that, let's create a material, the steel material. So those are the command lines for the material. We create a material tag, so a unique identifier within OpenSees for the material class, or object in this case. We're going to give it 210 gigapascals. This is pascals. The Poisson's ratio is actually unitless, so nothing there. And the mass density is going to be in kilograms per meter cubed. Sorry for my US listeners, I'm using SI units. Anyway, so we add the material. So if we execute this, nothing actually happens, but something we can do is we can start adding, let's go for the print model command. So this is going to give you information about what is going on with the domain. So right now, current domain information, we have added no elements, no constraints, no single point constraints, no multi-point constraints, no load patterns, and there's no parameters. So there's nothing in the model. We added the material, but that's handled a bit differently in OpenSees, so it's not going to show up within this unless we have elements later. So we'll see those pop up later. Okay, so what do we do now? We want to add, and here we want to add the nodes. So how do we add the nodes? We're going to use a very handy function in gmsh to OpenSees. We imported gmsh to OpenSees as G2O. Okay, so we're going to use a function called get elements in physical group. Elements and nodes in physical group. So this function receives it, and it's a verbose name so that we know what it's doing all the time. So I'm going to grab all the elements and nodes that belong to the solid physical group. I'm going to add the gmsh model. So what this does is it looks at the gmsh model that I loaded up here, and it's going to look into the physical group called solid, and it's going to return a bunch of information. So the information I get back from this, there we go, I'm going to get element tags, node tags, element name, and element number of nodes for all the elements and nodes that belong to this physical group. So let's see this in action. I'm going to print here the element tags. So once I execute this, and before I get the OpenSees data, I'm going to see all the element numbers that belong to that physical group in one giant list. If I do the same for the node tags, you'll get the node tags. Now this is in a format. These are all the nodes that belong to that group. Some of them, as you can see, are repeated, because the way this is done is for each element, you basically make a list of all the nodes that belong to that element, because elements belong to physical groups. Nodes don't belong to physical groups. So that you have to kind of get them through the elements that belong to physical groups. Don't worry about this. This is just to show you what we're getting out of the output. Now, there's a handy little function in gmsh to OpenSees that I've written that allows you to add nodes to OpenSees just by a simple call. So I'm going to, all the node tags that were defined here, I'm going to add them as nodes into OpenSees, and it's going to take care of not duplicating nodes, right? So once we do that, if I execute this, what you're going to see is that now the print model command is giving me all the nodes out. This is what we want to see. So all the coordinates of the node. It's a large and verbose printout. Okay, so now we have the nodes loaded into the OpenSees domain. That was very easy. This is a very simple and very easy to read script that we have here. So we got basically the nodes that we got that belong to the solid physical group, and we added those to the OpenSees model. Now, depending on if you're doing more complex analyses, there's other things that you might want to do before you add the nodes to OpenSees, but this is the basic thing. Okay, next we want elements, and in this case what we're going to do is a different strategy. We are going to, so the way this works, if you remember element tags and node tags, these two lists go together with each other. So it has the element tags, and the node tags are the nodes that correspond to that element. That's basically what's going on. So what we're going to do is we're going to iterate the element tags like so. So we're going to iterate together the element tags and the node tags lists so that we get the tag of the element and its nodes. And with that, we have all the information we need to add a tetrahedron element. So here, this is how we do it. We call the regular OPS element function. This one is inside the OpenSeesPy module. We're going to add 4 node tetrahedrons. We're going to add the element tags and the element nodes. If you don't know what the star means, it just means expand this list of 4 nodes into 4 arguments within the function, right? So it's a nice compact way of dealing with the element nodes. And we're going to assign those elements the solid material tag. At this point, I'm just going to run and see what's going on. And we can see now that we've added also some elements. This is getting long. So we have the nodes first, and then come the elements. You can see no body forces. It's 4 node tetrahedron. That's the element number. And you have 4 nodes, and the material information is not printing out at this point. Anyway, so let's continue. What's next? We need to fix the nodes that belong to the fixed physical group. So the way we do that is we're going to call the get element and nodes in physical group function once more, like so. But now we're going to use the fixed physical group name, right? And we're going to call another simple function from gmsh to OpenSees that's called fixed nodes, that takes node tags as an input. It's going to fix all the nodes that come in this list, taking care of the duplicates. Remember, these are the nodes that belong to the element. So these are the element. Basically, you're looking at this fixed physical group, and it corresponds to one face, to this face over here. So if you look at that group, it has all these triangles there. So the elements in that group are going to be these triangles. You can do stuff with those, but and the nodes. So if I look at the element tags, those are going to correspond to the node tags. There's going to be the same length for those lists. Okay, so for all those nodes that belong to this group, I'm going to call the fix function, and then I've added a little cute thing here. Is you can call the DOFs, the degrees of freedom, by XYZ. So if you just want to fix in X, you just write X. If you want to fix in the XY plane, you write XY. If you just want it sliding in the horizontal direction but impeded in the vertical direction, you just write Z. In my case, I just want to do XYZ so that it's a complete fixity. So let's go now and execute this. And you'll see that by the end here, we've added also some single point constraints for all the nodes. So you can see, for example, node 2 has all its degrees of freedom restricted. Let's go back to the mesh. Let's see if we can find node 2 somewhere. It should belong to that, to this physical group here. You know, the colors over here are messing me up a little bit. So we can go and let's go by color by elementary type. Let's go like this, and then node 2 should belong to that group. So it's 1 over there, 1 over there. That one is the axis. Somewhere, oh, there it is. So that's 0.2. Also 0.217 belongs to that physical group, so we should get constraints for node 217, and there it is. DOFs 1, 2, and 3, x, y, z are constrained, are fixed. Okay, good. So we're almost done. The other thing that we need is we need to add a load. Okay, so we're going to add a load. We're going to add that load manually. So first of all, I'm going to create, so loads need to live within load patterns, and load patterns need to have a time series associated to it. So in order to add a load, you first need to add a time series that's going to modulate the load pattern. In this case, let's add a constant time series so that the load is constant. That time series has its own tag, and then I'm going to create a load pattern that's going to contain the new load. It also has its own tag, and you can see I'm using the linear. It's not linear in this case. Let's just call this TS tag, time series tag. And then finally we add the load. So we're going to add a load where we said in our domain we wanted to add this in node 249 over there. So let's do that. Let's call the ops.load command. The loaded node is going to be 249, and let's add the values for the x, y, and z components. For now, let's just leave the x0, y0, and fz. We're going to push this into the model with 10,000, whatever. This should be newtons. Okay, so we're done. Now what we need to do is I'm gonna comment that line out so that I don't get so much output into the screen, and we need to set up the analysis. So I'm going to do a basic static analysis. We're going to have the UMF pack system, and we're going to number the DOFs using the plane numberer. We're going to also use the constraint handler, the plane constraint handler, that's going to take care of removing rows and columns of the stiffness matrix in order to enforce the fixities. More coffee. And then let's use the load control integrator, like so, with a load factor increment of 1. And let's use the linear algorithm, because we're doing a linear analysis, so we don't need anything else. And let's declare our analysis to be a static analysis, and we are going to call ops.analyze with one step. And that should be it. If we execute this, yeah, we get nothing. I removed all the screen output, so I commented out this line. So nothing's going on. Let's take a look at what the nodes are doing, okay? So let's iterate the nodes and see their displacements. So let's go for node in ops.get node tags. This should give me all the defined nodes in the OPS domain. So let's do print f node number, and let's just print the node like this. If I execute this, I'm just going to get all the node numbers, but I also want to print out the displacements. So for this node, I'm going to ask for its displacements. It's going to be ops.get disp of the node. So let's do disp equal like this. Get node disp, sorry. I always miss. I think it's get node disp. No, it's just node disp. Node disp, like this. There we go. So now for each node, we're getting displacements, and we're getting non-zero displacements. This is fun. This is useful. We can do stuff with this, but it's a 3D model. We really want to, visualize. So for that, we're going to use another little tool that's in gmsh to OpenSees. We're going to use a function called visualize displacements in gmsh. So that's all we're going to do. And you call that with a gmsh model, and you need to tell gmsh when to run. So you could call this several times and visualize several things. So once you're done setting up the visualization that you want to have, then you call gmsh.run.fltk.run, and then at the end of the script, just to be nice, you can call gmsh.finalize. Once you do that, this is what you get. This is what you get. You get, yeah, the displacement field. So the displacement field, let's do something here. What I did there is post-processing. I'm getting this displacement view, and let's set some options here. Let's the aspect, let's set it to displacement, and we can add a little factor there so that we can see what the deformed mesh looks like. Yeah, this is looking nice. And yeah, so this is pretty much it. Now you can play around with this. So you can do stuff like, okay, let's close here and let's add the load instead in the X direction, like this. Yeah, now this looks different. Look at this. Ah, that's beautiful. That is beautiful. Change the aspect to displacement and give it a little displacement factor so that it looks displaced. The displacements are tiny. This is a steel block and we're adding a point load at the top. So you're getting, you know, you're adding a singular force there, right? So it's a singularity X. So you're gonna have a lot of displacement there, and then the rest is just gonna follow along. This looks so nice. So that's the usage of this gmsh to OpenSees module that I'm putting out there for you. Play around with it. I'm gonna come up with some new tutorials doing some different things, how to turn this into a beam and add different fixities. Those are tutorials coming up. Let me know if there's something you're interested in that I might make a tutorial on, and follow, like, and all of those things, and just interact with me. I'm also on Twitter if you want to look at me there, and take a look at the links that I've put in the description so that you can follow me everywhere where I am. Okay, goodbye for now. Thanks for everything. See ya.